the architecture, the register organization of 8086 microprocessor. So here the complete registers. So 8086 has 14 16-bit registers. So out of 14 registers, these are divided into two groups. These are divided into two groups. That is, one is general purpose registers. Second one is segment registers. Next, pointer and index registers. And finally, flag registers. We can see the names of all the registers here. So all these registers are 16-bit registers. All these registers are 16-bit registers. They can store 16-bit data or address temporarily. Coming to general purpose registers, here these are divided into two 8-bit registers, higher byte and lower byte. So general purpose registers can be used as either 8-bit or 16-bit registers. Let us see in brief. So this is about the total registers. So general purpose registers 4, segment are 4, index and point registers are 5, and flag register is 1. Totally 14 16-bit registers. And coming to general purpose registers, so there are 4. Names are AX, BX, CX, right, and 16-bit registers. So the names of a accumulator: AX is accumulator, BX is base register, CX is count register, DX is data registers. So here H represents 8-bit higher byte, L lower byte, and X represents 16-bit. And here these AX and BX, CX, DX general purpose registers are used in arithmetic and logical operations, and each and every register has a special functions. So AX accumulator used to hold the operand and results of operations like mul, div, IO operations, and BX is used to hold address in some addressing modes, and counter, it is used as a default counter to perform some operations: loop, string, rotate, string operations. And DX is called data registers, and it is used to hold 16-bit IO port address during IO operations. It is also used to hold a part of the result from mul and division operations. That is special functions of general purpose registers. Coming to the segment registers, right? There are 4 segment registers. As 8086 microprocessor uses memory segmentation scheme, in that all the memory is divided into fixed size of segments, each of size 64 kilobytes. The segment has a starting address. So this one, the segment register holds the starting address of a segment, and the instruction pointer points address of next instruction to be fetched from the code segment. Okay, that is. And coming to index registers, so here there are 2 index registers are used to hold 16-bit offset address of data segment, that is stored in SI, source index, and extra segment, it is stored in destination index register. So here these 2 registers are used in string operations, which is index register, source index and destination index registers are used in string operations to hold the offset address of a source string and destination string. So here source index registers holds the offset address of source string in data segment, and DI holds the offset address of destination string in extra segment. For example, like this, we will denote like this: ds colon hi, es colon da. Here, while performing string operations, we have to concentrate on di flag. Is a flag which is in flag register di, direction flag. So based on the selection, if di is equal to 0, then we call it as auto decrement operation, and if di is equal to 1, then we call it as auto increment operation. So it will select the di will select the mode auto increment or auto decrement. Based on that df value, the si and da registers contents will be increment or decrement during string operations or string manipulation while executing string manipulation instructions. So df is equal to 0, it is increment mode. Df is equal to 1, it is decrement mode. And next, coming to the stack, that is pointer registers. We have three pointer registers: instruction pointer, already we have discussed, and stack pointer and base pointer registers. So the base pointer register is used to store the offset address of a stack segment, and the stack pointer in 8086, the stack is there, that is a last in first out fashion and last in first out structure. In that, the top of stack address is stored in stack pointer. SP will point top of stack. Next, coming to the flag register. Coming to the flag register. So the flag register, use of flag is identity. So in 8086 microprocessor, it performs so many operations. After operations, it will get the result. The result has a status, that is, we call it as the result may be 0. During the operation, there may be internal carry, and there may be the result may be a positive or negative, and there may be a parity, even parity and odd parity, or the result may exceed the specified range, like that. So all this information is stored in flag register. It is also called program status word. So in 8086 microprocessor, it has a 16-bit flag register. Out of 16 bits, there are 9 flags. The 9 flags are divided into two groups. That is, one is condition flags or status flags. Another one is control flags. Right? Coming to the condition flags. So the condition flags are will modify or update based on the result. We cannot modify the condition flags. They will automatically update after execution of the instruction after performing operation. Coming to the 6 flags are carry flag, parity flag, auxiliary carry flag, zero flag, sign flag, overflow flag. And coming to the control flags, these flags controls the operation of the processor. See, these flags controls the behavior operation of the microprocessor. They are direction flag, interrupt flag, trap flag. This is the structure of format of a flag register. This is flag register format. Right? We have 16-bit register. Out of 16 bits, 9 are there. The into represents the undefined. So this diagram shows the function of each and every flag. When the flag will going to 1, that is set, and when the flag is going to 0, that is reset based on the result. So coming to carry flag, the carry flag is set to 1 if there is a carry generated in addition or subtraction. So that is the carry flag when during operation, if the result exceeds MSB bit, if there is a bit out of MSB, then it will go into 1 during addition or subtraction. Coming to parity flag, so if the result is having even number of 1s, then the parity flag will become 1. For odd number of 1s, it will become 0. And coming to auxiliary carry flag, so the auxiliary carry flag is going to set 1 if there is a internal carry from lower nibble to higher nibble, that is d3rd bit to d4th bit during operation. Okay, 0 flag. So 0 flag is going to set to 1 if the result is 0. That means if the result contains all the bits are 0, then it will go into 1. Next, sign flag. The sign flag indicates the sign of the number or the results. So the sign flag is equal to 1, indicates the result is negative. Sign flag is equal to 0, indicates the result is positive. So the sign flag is the copy of the MSB of the result. Overflow. So it is the overflow is set to 1 if the result of signed operation overflows into sign bit. Right? These are all the 6 flags, condition flags. Coming to next one, direction flag. The direction flag already we discussed. That is, it is used to select the mode, increment mode or decrement mode, auto increment mode or auto decrement mode. So in that mode, the contents of SA and DA register will be changed. So if DA is equal to 1, then SA and DA registers are automatically decremented after the execution of string instructions. It is, we call it as auto decrement. So in this, the string is processed from higher address to lower address. And if DA is equal to 0, DF is equal to 0, the SA and DA registers are automatically incremented after execution of string instructions. This is called auto increment operation. In this what happens? Uh, in this, the string is processed from lower address to higher address. And interrupt flag. So the 8086 microprocessor has hardware interrupts and software interrupts. Software interrupts is nothing but by executing an interrupt instruction that, uh, that causes an interrupt to the microprocessor. Then we call it as internal interrupts. External interrupts means causing the interrupt by applying an external signal. We call it as external interrupts. So 8086 microprocessor has internal and external interrupts, and there are other interrupts, maskable interrupts and non-maskable interrupts. So for non-maskable interrupts, the 8086 microprocessor, it may or may not respond to those interrupt requests. So those maskable interrupts are controlled by this interrupt flag. So if IF interrupt flag is equal to 1, then the maskable interrupts are recognized and processed by the CPU. Otherwise, the maskable interrupts are ignored and not processed by CPU. That is, in 8086 microprocessor, it has two hardware interrupts, NMI, non-maskable interrupt, and another one is interrupt request, INTR pin. The INTR is the maskable interrupt. If IF is equal to 1, then the 8086 microprocessor recognizes interrupts through INTR pin, or else if IF is equal to 0, it ignores the interrupt request through INTR pin. Coming to the last flag, that is trap flag. So trap means diverting, like diversion, right? So on the way. So here, this flag is used in debugging. So what happens if the trap flag is equal to 1, then the microprocessor will execute only one instruction and waits for the input. It will wait for the input from the user, right? If we give input, and it will execute another instruction, and it will wait, and it will show the results of or status of the registers and memory contents. After execution of every instruction, it will show the contents of the register and the memory, right? So that's why it is called single step mode, executing only one instruction, right? So if TF is equal to 1, then the microprocessor 8086 will enter into single step mode. Otherwise, if TF is equal to 0, the 8086 microprocessor will execute all the instructions in the program. So this is about the flag register organization and flag register of 8086 microprocessor.